Let's understand complex numbers in this video. Have you ever wondered what the square root of -1 means in math? Or why engineers use imaginary numbers in circuits and waves? This idea leads us to complex numbers, a useful extension of real numbers. A complex number has two parts, a real part and an imaginary part, written as z equals a plus ib. Here is the symbol for the square root of -1, meaning I squared equals -1. The real part is a and the imaginary part is b, and either part can be 0. So every complex number can be seen as a point on a plane, with the horizontal axis for the real part and the vertical axis for the imaginary part. For example, 3 plus 5i has real part 3 and imaginary part 5. 5 is purely real with imaginary part 0, and minus 2i is purely imaginary with real part 0. We can represent complex numbers in 4 common ways: the Cartesian form, the polar form, the exponential form, and as vectors. The set of all complex numbers is denoted by C, that is, all numbers a plus ib where a and b are real. Two complex numbers are equal when their real parts are equal and their imaginary parts are equal. The powers of I repeat every 4 steps, since I squared equals -1, I cubed equals -I, and I to the 4th equals 1. Now let us look at operations you will use often, starting with addition and multiplication. To add complex numbers, we add real parts and add imaginary parts separately. To multiply z1 equals a1 plus I b1 and z2 equals a2 plus I b2, the product is the real part a1 a2 minus b1 b2 plus I times the quantity a1 b2 plus a2 b1. The conjugate of z equals a plus ib is z bar equals a minus ib, and the modulus is the distance from origin. Z equals square root of the quantity a squared plus b squared. In polar form, z equals r times the quantity cos theta plus I sin theta, where r equals modulus z and theta is the argument or angle from the real axis. The Moivre theorem then says the quantity cos theta plus I sin theta raised to the power n equals cos n theta plus I sin n theta. Let us try some solved examples to make this clear. Question number 1 asks, let a and b be roots of x squared plus x plus 1 equals 0. Find the equation whose roots are a to the power 19 and b to the power 7. The original roots are the non-real cube roots of unity. Call them omega and omega squared, and omega cubed equals 1. Reduce exponents modulo 3. 19 mod 3 is 1, so a to the power 19 equals omega, and 7 mod 3 is 1, so b to the power 7 equals omega squared. So the new roots are again omega and omega squared, and the quadratic with these roots is x squared plus x plus 1 equals 0. Question number 2 asks, dividing f of z by z minus I gives remainder I, and dividing by z plus I gives remainder 1 plus I. Find the remainder when f of z is divided by z squared plus 1. The remainder must be a linear polynomial a times z plus b. So substitute z equals I and z equals minus I to get two linear equations. Substituting z equals I gives a times I plus b equals I. And substituting z equals minus I gives negative a times I plus b equals 1 plus I. Subtract the second equation from the first to eliminate b. This gives 2a times I equals -1. So a equals -1 divided by 2i. Remember, 1 divided by I equals -I. So a equals I divided by 2. Now substitute a equals I divided by 2 into ai plus b equals I. Compute I times I equals -1. So -1 divided by 2 plus b equals I. Hence b equals I plus 1 divided by 2. So the remainder is I divided by 2 times z plus the quantity 1 divided by 2 plus I. Question number 3 asks for complex numbers z satisfying arg of the quotient equals pi divided by 4 and a modulus condition. We set z equals x plus iy and simplify. Rewrite numerator 3z minus 6 minus 3i as 3 times the quantity x minus 2 plus I times y minus 1 and denominator similarly as 2 times the quantity x minus 4 plus I times y minus 3. Since 3 divided by 2 is a positive real, the argument condition reduces to argument of the numerator minus argument of the denominator equals pi divided by 4, which leads to a real equation after setting the real part equal to the imaginary part of the quotient. Working through the algebra gives the circle equation x squared plus y squared minus 8x minus 2y plus 13 equals 0 for the first condition. The modulus condition becomes the circle quantity x minus 3 squared plus y plus 1 squared equals 9. Subtract the two circle equations to get a linear relation x plus 2y minus 6 equals 0. Substitute back and solve the resulting quadratic for y using the quadratic formula. You find y equals 1 plus or minus 2 divided by square root of 5 and x equals 4 minus or plus 4 divided by square root of 5. So z equals 4 minus or plus 4 divided by square root of 5 plus I times the quantity 1 plus or minus 2 divided by square root of 5. So what do we learn from this? Complex numbers extend real numbers by adding an imaginary part. They can be handled algebraically and geometrically, and their operations follow clear formulas. Let us quickly remember. Z equals a plus ib, conjugate z bar equals a minus ib, modulus equals square root of a squared plus b squared, and polar form links r and theta. Keep practicing problems, use the Argand plane for geometry, and use polar form for powers and roots. Learn at your own pace. And if you want more examples and practice, explore related lessons on EduRev for friendly study support.